Hello and welcome to today's Wolfram Institute live stream. We're joined with Chase Marangu, and he will be talking about cellular automata on uh, non-regular lattices, or lattices are not just the square grid. Uh, so, Chase, take it away.
All right, so let me share my window here. So I'm just going to follow along what I wrote for my community post here. So as you can see by the hero image, we experimented with other grids, and my mentor and I kind of sought to find like a decent way to generalize the square grid cellular automaton to other regular tilings. So the original Rule of 30 is really famous because it generates chaotic behavior from a relatively simple set of rules. And we found some similar rule sets for other grids. When we were deciding how to generalize the 1D cellular automata to other grids, we ran into a problem that these grids are two-dimensional, and sometimes there isn't a nice way to assign rows and columns. So if you see here, even for a grid of hexagons, there are actually infinitely many ways you could set for having hexagons on the same line. So
Okay, can you zoom
what we
in?
did is we just said, yeah. Can you see this now?
Uh-huh.
So we decided to just go for the two that were most aesthetically pleasing and interesting. So a line that goes straight through the corners and also a line that goes straight through the edges. That's what we did for the hexagons. And we did the same for triangles and for squares. And how we assign neighbors, where we just looked at what shares edges above the previous cell or corners. And so, yeah, um, we found that a lot of the rule sets generate relatively boring behavior, but there are a few that there were quite a lot of Sierpinski triangles that we generated uh, due to the fact that when you XOR the two neighbors above, it generates the same um, yeah behavior. And um,
Okay,
yeah,
so just a quick question. So like the slanted squares, like what's the valency between rows, I guess? Like how many inputs does each cell have?
it gets three inputs.
Okay.
So it would be the three that share an edge or a corner.
Okay, so
Yeah,
each one
whereas
gets its
the
inputs
original
from the three above.
exactly, whereas with the original square grid, it's just the three that share an edge or a corner above. That's how we defined it.
Hmm.
Um, and we thought that would be a natural way to generalize it to other grids. And yeah, so with the hexagon tiling, with the um, corners aligned with like the vertical line, we found that actually they just correspond directly to uh, the logical operators on two input bits. So there was this really interesting kind of one-to-one correspondence with that. So XOR and XNOR actually they generate kind of like inverted of each other, but they have the same behavior. And with if you have one that's just always false, the operator the logical operator that's always false or always true, well, obviously it's just going to always turn the cells off or always turn them on. And there were also a lot of other interesting behavior we found with these, like with with an and we found that it just kind of generated little. I mean, with and it just generated sort of like little icicles because if you have to have both cells be on, otherwise it kind of dies off. Can you see this image here clearly?
Yeah, can you, oh, this is on the web, right? So it's hard to zoom
Oh
in.
yeah,
Um,
yeah. I
oh,
have
I
a
see.
demo. I'll bring
Oh,
it.
okay, great.
Maybe we can. Yeah.
So this is the hex
Anyways, and
hex tiling where the orientation is each hexagon is adjacent to the two above it.
exactly, yeah, they were real. This was one of my favorites because each one corresponds directly with just a logical operator onto inputs, and so it's kind of a fun way of visualizing the logical operators. Um,
Yeah.
yeah, so yeah, and that was one of my favorite ones that we made. And then this is the same thing, except instead of random initial conditions, a we have a single cell initial conditions, which is really fun because this was one of the first ones we had gliders. So
Uh-huh.
they would kind of, gliders, they kind of just translate across each iteration and they don't grow or die. So that was interesting. And we also had a lot of Sierpinski triangle again with the XOR and XNOR, which is similar to some of the rules on the original square grid. And yeah, that was after that I got onto the rule sets with triangles, and these ones got a little messy because you have so many neighbors. Uh, so it became yeah, you have 5 neighbors for each. So it was they were kind of all over the place, and it was harder to find a rule set that looked interesting because you would have to make sure everything's symmetrical and stuff. But yeah, we just finished it up for the heck of it, and yeah. Anyways, here were just a few of the rule sets. There are obviously over 4 billion rule sets, so it's not
What?
like the
So
hexagons where
what's the neighbor
we can
count
put like,
for the triangular lab?
yeah, there are 5 neighbors,
So
which are
each
the
one
five.
has 5 inputs.
Yeah, and that's why there were so many rule sets. Whereas with the hexagons, you only had 2. So there are 16, 2 to the 2 to the 4 rule sets. So we can fit them in a nice grid here and visualize every single rule set, which was pretty nice. But with the triangles, there were so many rule sets that um, I mean, it was hard. You can't visualize all of them all at once. So yeah, it was a little more chaotic.
Right, right. Was this a random search into the rule space there?
Oh no, these were just a random. This is just like I just kind of linear interpolated, and just selected a few.
Uh-huh.
Unfortunately, the few I selected didn't. There's definitely symmetry in the automaton itself. It's just the way I selected rules because I finished triangles last. I was trying to wrap up the project. Makes
Yeah.
it look like that they have to develop, but that's not the case. This was just a random, just a few selected from the rule set. Anyways,
So can
and
yeah. Can you show the neighborhood analysis for that? I guess it's on another tab, but well, what is the triangular tab? And what are the inputs to it? So
yeah, so for example, let me just zoom in on, if you have the triangles where like they're sort of like sideways rhombuses is what I'll just call it, a
yeah.
horizontal rhombus. If this triangle, like in the row above it, it has 5, so it would be sorry, uh, for this triangle you have um, this one, this one, this one, this one, and this one, I believe.
So for this one,
Yes,
it's
5 that are.
this one, this one, this one, and this one.
I didn't see your mouse cursor, but yeah, they were
Oh,
it's just the 5 that are in a row above it, and yeah, if you
can you see my
yes,
my squiggles here?
I oh no, unfortunately no, I can't.
Oh,
Yeah, I'm from Zoom Web, so I don't have as many features.
I see.
But yeah, anyways,
Uh-huh.
um, yeah, if we can get to the demo though, if you're ready, for that, or unless you want me to go over
Oh,
something
you
else in
keep
the
going. Just trying to get a flavor for it.
yeah.
Yeah. Try not to get into the weeds though.
Yeah, that was basically it. And yeah, so yeah, my favorite though was definitely the the rule 9D on the hexagon grid, which generated this sort of Sierpinski triangle. And it's also what I used with random initial conditions. It was the hero image, and you can see there's a lot of complexity, sort of similar to rule 30 on the square grid.
Right, right. And that this is where each hexagon is adjacent to three above it.
Exactly.
Mhm.
That's exactly how that one's defined. Yeah.
So you're implementing Rule 30 on a hex grid.
This is rule 90, but
Rule 90.
it behaves similarly to rule 30 on the square grid. So yeah, and I have the notebook, and I can. So I think we can go ahead and. So yeah, you can if you want to. If you, I can send the notebook. It's published on Wolfram Cloud, and you all can try it out.
Awesome.
Maybe I should just send the link in the Zoom chat.
Sure.
Let's see here. You'll have to make a. I think you need to make a copy before you can execute it. But here, let me just send this notebook in the Zoom chat.
Version.
Oh yeah, let me just. Yeah, recursion. Gotta love feedback. Yeah, feedback recursion.
We're all nerds here. That's good.
Okay. Yeah, let's. Yeah, so to use the notebook, essentially what you do is you just you can choose a seed type. Seed type. My favorite are using a single live cell or random initial conditions. Those are my two favorites personally. So and then you choose the rule numbers and and the the tiling type by changing here. So um, if you want the hexagon grid with two neighbors, you would choose number 6, and if you want the hexagon grid with 3 neighbors, we would choose 5. So if I'm remembering how to do this correctly, I will just run the cells now. I will note I clear all the tokens every time. This is because I had a little bit more of a procedural programming paradigm when I was putting this project together, which is not necessarily how you're supposed to use Wolfram language, but it worked out well in the end. So, and you can, and yeah, we'll generate the images of this automaton. Yeah.
Cool.
Actually, my bad. I think to change the rule number, you have to change it somewhere else in my code. Yeah, but this will just show a few of the rule sets with the hexagon grid. And yeah, does anyone have any questions or want to see a specific rule set on a specific tiling?
Um, let's look at Rule 30 on this hex grid.
Yeah. Okay. Cool. Yeah. So let me change the rule number.
Yeah, with random initial conditions.
Yeah. Okay.
Well, with the with both, like with the single one
Okay, okay, yeah,
and
we
then
can
later.
start.
Yeah, single cell and random. Let me see here. I think I added a feature that draws out this nice with like the number of rays, and yeah, here we go. I think I'll have to edit somewhere here. All right, I think this will do it. Let's see here. We'll start with a single cell initial condition, and Yeah, I'll just let Wolfram Cloud take his time as it computes this. But I think we broke something. Oh dear. That's funny. All right. Let's just go back. Okay, so okay. Yeah, we change it right here. All right, I think this was it. I just have to figure that out. Okay, so, and let it render. But yeah, here you can get a little sense for what it looks like. So. All right, here's rule 30 on the hexagon grid. Actually, it's not as interesting on the hexagon grid as it is on the square grid. It just kind of has these sort of like.
Oh, I disagree. I think it's more interesting.
Yeah, well, it's much more, I think it's less, suffice to say, it's much less chaotic. It's much more orderly. I think, in my opinion, my favorite rule set on the hexagon grid was rule 90, for sure.
Rule 90 is the same on a hex grid as it is on a more neighborhood.
On a which
It
one?
just looks more compressed on the standard grid. It just looks more compressed and cute.
Interesting. Rule 90 also does the, oh yeah, you're right. It does, it's sort of just like Sierpinski triangle.
Yeah.
Type of, yeah. Yeah, so this
So
is like
that's
a few of the rule
interesting.
sets.
So the topology of how the hexagons are connected is different than the topology than the square grid is connected to the three above it. In the sense that
Yeah.
that they both have like three neighbors to the north of them, but in the topology of how the hexagons are connected, that you have like little triangles.
Yeah, exactly. That's yeah. The way we define it, the neighborhood, it kind of yeah. But some of these, an interesting thing that happens is some of these do have kind of some of the rules on different grids will have the exact same like connection, like neighborhood graph. Like yeah. So yeah, that was yeah. And if yeah, my personal favorite is rule 90, but we can do that one here. We can look at random initial conditions too. So let me run that here. With random initial conditions, here's what rule 30 looks like on the hexagon grid. We'll just give them a render. Yeah, here we go. It sort of does similar to, I forget which one it was, but on the original, but yeah, logical, I think logical not on the two neighbors hex grid is similar to what rule 30 is here. Rule 36.
So rule 30 is basically the opposite of the left cell in whatever mapping you're talking about, unless the center and right cell are both 0.
Interesting.
That's so basically the reason it turns into a striped configuration when you tilt, because a hexagon grid is sort of like taking the square grid and just tilting it 45 degrees and running it that way. And so when you tilt it, you wind up aligning your center and right cells in a way that they're more likely they get you get that association with the two, they establish themselves as two zeros more easily. And then the striped pattern is just a reflection of that heuristic of the opposite of left, unless to the center and right are zeros.
Interesting.
Yeah, it's all, I think this is a sort of my general observation is that there's we need to separate the idea of the rules from the geometry of the system within which they're placed, right? That's what your paper is about. And I kind of think of it like of structural aliasing. And so like some rules actually, there are a lot of rules that then wind up to having the same visual behavior in some systems, in one system of structural aliasing versus other rules in other systems of structural aliasing. And so I think it's helpful to sort of separate out the rules from the system in which they're implemented and studying those dynamics. So the idea that Rule 30 is a chaotic rule, I sort of push back on that. I think it's really only a chaotic rule when it's in a certain system, a certain geometry. But in other geometries, it's actually a very stable and non-chaotic rule.
Exactly. Yeah. My mentor, he wanted to also, for this project, to explore potentially uh, looking at, say, the graph, the neighborhood graph, rather than the tiling. But we found that, like, yeah, that was outside of the scope of like the 2 weeks that we had to work on it during the summer. But yeah, that was.
Yeah, like in a very general sense, we could define the neighborhood with reference to any previous cells, right? Any previous three cells.
Oh yeah,
And
absolutely.
I like this idea of creating like a really general automata or graphing tool that lets us define what those three sort of neighborhood cells are. I mean, there are reasons why the adjacent cells are the obvious neighborhood, right? When we study biological systems or systems in nature. But, in theory, they could be anywhere. And in a situation where you have like folding of tissue, for example, or folding of material, the relevant neighborhood cells could be, in a very different location from the ones that are just most proximate to the cell that you're updating. So that could be a reason to generalize the sense of a neighborhood.
Yeah, that does remind me, like in 2D cellular automata, smooth life is really popular, and the idea with smooth life is, I think, the main idea is just essentially to have a much larger neighborhood that involves cells that aren't necessarily tangent, adjacent to a given square cell. So yeah, and it does generate kind of, see, these are very like discrete patterns, and you can see the individual cells a lot. With smooth life, you often see sort of more, I don't know how you would say, well, smooth kind of blobs that kind of morph around. So yeah, it's yeah, because yeah. All right. Well, yeah, so that's, yeah, anyways, that's essentially how you use my notebook. Is you can choose the seed type, and then you would change the rule numbers in the right here. So yeah, and you all are free to play around with it. I think, yeah, I shared the link to the Zoom chat.
Can you
Does anyone have any questions?
show us Rule 90 in
Yeah,
detail?
on the hexagon grid. Yeah, personally, the two hexagon grids, both horizontal and vertical, were my favorite. So if we go with a single live cell, I think we'll say, we'll just give it some space.
Yeah, I like Rule 37 and, 45. Rule
Mhm.
38 has some interesting characteristics. What did Steven think when he saw these? 'Cause
Oh yeah, in the mid summer school checkup, I showed him the hexagon grid with just the two cells above it and how those corresponded nicely to the 16 logical operators on two inputs. And yeah, he was pretty happy about that, and he was really excited to see about like how far we could take the scope of the project. Yeah, it was. Yeah, he of course was the one who originally suggested the idea of um, 1D cellular automata kind of generalized to other grids, and yeah.
Okay. Okay. So Rule 90,
Anyway, so
that's the Sierpinski style, very
yeah,
regular.
exactly. But when you do like my hero image and you do random initial conditions, you get some other behavior that kind of has like, I don't know, I guess you could call them like frog feet. They sort of look like frog feet to me. Sort of kind of growing, upwards, so like some kind of fractal tree behavior. It's really fun. Rule 90 on the hexagon grid is definitely my favorite. And yeah, if you set in that random initial conditions, um,
Yeah,
you
I've
can see.
referred to them as little appendages.
Yeah,
Uh-huh.
yeah, you could call them, yeah, appendages, I guess.
But I mean, it does mimic when you see them on random initial conditions, it does mimic sort of plant-like growth or, there's something very profound about XOR and the pattern that it creates feels really like something we see in nature very often.
Yeah, XOR, yeah. It's almost like it kind of, XOR is kind of embeds like John Conway's Game of Life too, where if you have no, well, actually, there's a little problem with that because if you have none, then one can be born. But the idea is that if you have one neighbor, then you can you can be born. But if you have two, then it kind of suffocates the neighbor above. So that's sort of, I think that's part of why like it overpopulation will kill a cell. Um, yeah, but one will allow them to be born. Sort of similar like to the S23B3 rule set of Common Scheme of Life. Anyway, so here's rule 90 on the hexagon grid. I can also something we might want to try is we can also do much bigger grids. This is just a few width and height. If you're interested, we could try like doubling the width and height and see what some of these rules look like. It might be interesting.
Yeah, let's try that. Get a
Okay.
better sense of the texture. Um, and I'm particularly looking out for like ones that are really random. But
Yeah.
I'm getting the sense that due to the topology of the hex grid, the way we're doing it with three neighbors, that it's that somehow forces it to be less random.
Yeah. I found that I think I found that in as our project with two neighbors was not enough to be chaotic. But the original through 30 on square grid is chaotic and that has only three neighbors.
Mm-hmm.
So kind of as this project, I think one of our sort of findings is the way we define neighborhoods. You need at least three neighbors to have chaos because none of the hexagon grid, which had two neighbors, were chaotic. Let me see here. We can say, I'm actually just going to generate one image here. So
Okay.
let's see here. Of just rule 90, and we're going to do like 9 times the size. This might take a little while. Oh yeah, that's nice. That's gonna be great. Okay. Oh, of course, it will take a little time to generate something that's 9 times. But yeah, here we go. Let's scale this up a bit. Yeah, so this is pretty similar to what my hero images had. It kind of just repeats like this because of the, the XOR, it just kind of, it grows and then it eventually overpopulates. So it kind of favors smaller scales. This does remind me a lot of the automaton lizard sort of. I think they might have figured out the how that one's scales work, like the actual automaton. But yeah, that was
So this is kind of
yeah.
chaotic in a way.
Yeah,
You never
well,
tell what's going to happen. I mean, there are, these triangles which are pockets of reducibility. Stephen would say.
it's chaotic because we put random initial conditions is why. But yeah, because when you do the normal initial conditions, we actually just end up with the Sabrinsky triangle. So I thought that was really interesting because with XOR, if you just keep repeating XOR, what you end up with is you just end up with a. If I'm, it almost kind of like, okay, let me try and actually, there's another way we can show this. If we start with two cells, where's my initial conditions? If we start with two live cells, I can show you what happened with XOR. It kind of does like a, if you ever do filter invert, it basically does that with the two. They kind of invert each other. It's not destructive. It kind of conserves all of the energy they both have, but it just turns it into, anyways, I'll show you with the two live cells. So when you had the, anyways, here we go. So,
Oh, is this on a
yeah.
on a wrapped repeating boundary conditions?
Yeah, this is on a repeating boundary conditions. Yeah.
Okay.
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 That's why I did it, because otherwise I would have to decide whether these are always dead or always alive or something, and I didn't want to be the person to decide that. So I was just like, it's the most neutral way of deciding. So yeah, if you see, there's just two initial points. They just kind of go through each other, and at the point where they kind of like, it's kind of like if two kind of waves interfere and they create a standing wave. Like there's sort of like just a standing wave here, but they just kind of continue on afterwards after like hitting through each other, the two Sabrinsky triangles. This isn't the perfect one because it kind of unfortunately coincides with it. Yeah. But if you change the width or height, you'll see it's just kind of.
Could you move the rightmost one like 3 or 4 to the left and run it again?
Move the.
Yeah,
Oh, this.
because they're equally spaced now, and having them be unequally spaced may do something different.
Yeah. So move this one.
Yeah, just move one of them. Yeah, just want to move them closer to each other or something.
Yeah, let me see here. The initial conditions. Which one was it? Keep two live cells. So yeah. So I'm saying the first one, we can say 5 to the right, maybe.
Yeah.
Yeah. And, okay. I guess 5 wasn't as much as we thought, but you can see it moved from here to here now. Oh yeah, so this is perfect. This kind of shows how, yeah. But you can see compared to last time, like they just kind of continue doing their own thing, and there's just a lot of kind of interference in the middle here where they were both overlapping.
The big black downward pointing triangles are making an interesting pattern. It doesn't seem that regular.
Yeah, that's
Yeah.
right. There's a
know,
little spot. There's a spot sort of, I can't really point on the screen, but you see one particular distorted structure that's kind of right there. Yep.
I see that. Yeah.
That's pointing at where that displacement, that
Exactly.
slight asymmetry is sort of echoing through in the overall structure.
Yeah.
I have this hypothesis that I'd love to see. I'd love to develop some code to test this. Is that with XOR, as long as you're consistently referencing the same two cells as you move along over time, that you get similar patterns. And it doesn't matter if those two cells are adjacent or if they're different cells. I think it may be the case. It's just that we might see so if you look, I think it's rule 120 and rule 30. Those are XOR with respect to the center and left and the center and right, rather than the left and the right. And with those, you just get the same thing, but it's just shifted. You see it rotated 45 degrees.
Yeah.
And I think that may be the case no matter what two cells you're referencing.
Yeah, I have found that the XOR definitely kind of, even if you had the two left or two right, center left, center right, it would still it kind of prefers symmetry, because of, if you look at the truth table of XOR and XNOR, of course, it's sort of evil twin.
Yeah.
They both have,
I mean,
truth tables.
Yeah. Now, my hypothesis, I would love to also see it completely wrong, because I'm sure that the results would be very cool to see. I'm looking at Dugan.
Yeah.
Yeah. You said that was rule 30, because that the same applies to the hexagon.
Oh, not 30. Sorry. It's not 30. It's 86 and 120. Anyway.
We can try rule 86.
You can figure it out. It's yeah. I used to know offhand when I was in my XOR obsession, but now.
Yeah. I also wanted to point out that everything here is just a repeat. It's just two Sierpinski triangles, and unfortunately, I chose a bad width and height because this one kind of spreads out widely pretty quickly. But it's essentially everything you see is essentially just two Sierpinski triangles overlapping. So if I removed one of these, maybe it'll help visualize it better. So if I say single cell initial conditions, and then we'll check out rule 86. You can kind of see the lines of this one Sierpinski triangle. Okay, the periodic boundary conditions are kind of making things a little more confusing here than they should be. But it's just two Sierpinski triangles overlapping. And when they overlap, it's basically the XOR of the two Sierpinski triangles. I think one of the hexagon rule sets kind of showed this better. So you see here, there's this one, and then the other one is the one that's just symmetric. So any chaos was just from them overlapping at odd angles, but when in the areas where one of them was off, the other one would still be on. So I think this is better shown with one of the rule sets that was on just the two neighbor hexagon grid. Anyways, so you said rule 86, I think. Maybe we can check.
So yeah, the rule for that is like you have the light blue dendrites trying to split at every node, and anytime two come together, they cancel each other out. Is that a fair assessment?
Which one? This rule 90 or 86?
This rule 90 here.
Yeah, exactly.
I don't know if it's 86. I spoke very quickly, actually.
Only one way to find out, right?
I think rule 120 is. Oh no, then it's not 86. 86 is special for other reasons, which I can't remember, but rule 120 is, I think, the other.
Okay, so that discontinuity on the right side is where the left side is wrapping around to like interfere with itself. Okay.
Yeah, this is just for the right side wrapping around. That's what's happening here. Yeah. Periodic boundary conditions. I chose them because I had previously programmed a lot of 2D cellular automata, and it's the easiest way to get things that look nice. Like, gliders will just go right around the screen. And
I think 86, I think 86 is the opposite chirality from 30. So where 30 is left biased, 86 is right biased.
Interesting. Yeah, we could confirm it.
Yeah, no, that's when it's striped. I think that's why I remember 86.
Let's see here. Oh, okay. So this looks sort of like a We should probably try this with random initial conditions. That might be a little more interesting.
Yeah, but that's not XOR. So anyway,
Which rule is this?
That was
This is
120.
120.
It's not.
Let's try 110 next.
Okay.
Oh,
good.
yeah.
What's up with 110?
How could we forget 110?
That's the Turing
What's
complete
special
one.
about rule 110?
It's Turing complete. So it has
Oh,
these
yeah?
like gliders that
Oh,
interact with each other and like bounce
oh,
off.
that'll be interesting. Okay, so yeah, 120 is definitely, no offense, but 120 is definitely not one of the most interesting rule sets I've seen on this grid. Yeah, let's see, 110. You know, just to confirm, maybe we should try it on the square grid, the original square grid, to make sure this is the same rule 110 that we're used to. This is rule 110 on the square grid, I
Why would
believe.
you, I'm curious to know, like when you say compared to the square grid, is that because the way that you're developing the plots here is different from how it would be done with rule plot? Or
The reason why is because the topology of the hexagons, it doesn't always, the three neighbors hexagons, it doesn't produce chaos as often as I think the square grid does. Would this be rule 110? Do you think?
Yeah.
Okay, cool. Let's see
think
what
that
it looks like on the hexagons. Anyways, yeah, I was just in my experience, the hexagons, they just seem to prefer symmetry, or with the exception of like the rule, I think it was rule 90, they seem to just prefer symmetric or gliders patterns. Whereas this original square grid, it has, especially with rule 30, it has all kinds of Turing complete rules. So that was just my experience, but I might have been, let's see here. This should be.
Could you show again the layout of the three neighbor hexagon thing?
The three
Which three neighbors?
Oh, yeah, here we go. Here, this. So it's just the three above it. That's all there is to it. Every hexagon has three above it, because those are the three that are edge or corner sharing in a row above. That's how we define it.
But here it's like you focus on like one hexagon and it has influence on the three below it, and the one to the left and to the right also have influence on the one below the first one. So you have this like
so
second
you're
order
saying-
effect of how it. I'm gonna draw on the screen. I know you can't really see,
Okay, cool.
but so this hexagon influences this one, and that one, and that one, and this one here also influences that one, and that's not something you get in a square tiling. Here, a square tiling influences these three, and none of those influence any of those. There's no crosstalk. There's no crosstalk, but here there is crosstalk. I don't know if I'm making sense to you, Chase, if you can't see what I'm drawing, but I hope I'm making sense to the audience and to the other people on Zoom.
Yeah,
Actually, Dugan, I don't know if this is the same thing, rather than drawing influencing, can you do it the reverse, influenced by?
Yeah. So this one is influenced by these three, and this one is influenced by these three, and there's sort of generational crosstalk, I guess.
okay.
Yeah, but that crosstalk is probably only relevant when you're using all three of the neighborhood cells to inform the next generation. but the crosstalk might not be. So there may be, I have to map this out, but the XORs, because it's only using 2 cells rather than 3, maybe that crosstalk is muted.
It's also interesting the way you have to. That's the order of updating. Let's say you know the state for this row, this ragged row, and then the next thing you have to do is sort of, now you know that you can update this one. Let's say, oh yeah, well okay, so you have to know this one over here. Let's say, but now you can update this one because you have its influences, and then you can update the next one down here. Whoops. I'll do
Wait, I think I know what you're talking about, even though I can't see what you're drawing. You're talking about how they're like, the rows are kind of like, they kind of alternate with like an sort of an offset on the x-axis, right?
mm-hmm.
Yeah, actually, so with the, I'm just gonna call it the vertical hexagon grid, there's
Yeah.
something a little bit, this is a little bit sad, but it's pointless because all the rules are just a subset of the rules on the original square grid, if I'm not mistaken. It's just it's just slanted of the rules on the square grid. So for like XOR, if you're XORing the 2 above, that's the same as XORing the center one and the right one, for instance. That they're equivalent.
Chase, you probably could see what Dugan's drawing with a bit of a time delay if you go to the YouTube stream.
Oh yeah, sure. But then would he be able? Okay, if I go to the YouTube screen, will it?
Yeah, I made sure to turn the sound off. That horrible
You're going to be
echo.
on the same screen though. Like you need to maybe check on your phone or something.
Yeah, you need to do it on a different
Yeah,
screen.
maybe I can just share the different tab. Let me just try that. Yeah, I'll share my the Chrome tab. Okay, let's see here.
While you're sharing, so Ellie, a thing that you said earlier, I thought was kind of interesting, but as often I was interpreting maybe backwards from the way that you said it, is having thinking separately about the connectivity from the geometry, right? And the thing that I wondered is, have you looked at all about mapping? You know, they're just systematically saying we've got these connectivities, and for each of them, what's the most natural geometry that they map onto?
Yeah, I haven't done that systematically, and I would love to. Yeah, I think it's a really interesting question to sort of separate out the rules from the geometry and see
You
it
know,
as
because
like a.
it almost is like there's lots of generalizations that Stephen didn't do for a new kind of science, really. Like even if we just stick with the same grid and have 3 neighbors, don't have be the 3 above, but 1 above and 1 5 to the left and 1 6 to the right.
Well, exactly. Yeah, that's exactly what I mean.
Yeah, for the generalizations, the reason why my mentor and I chose just the adjacent ones is because we thought that was the most natural, direct generalization of the square grid. And we thought if we're going to explore different rule sets, there's a lot of ways you can define them. But if we start generalizing too much more, then we would have to have generalizations on the original square grid itself too. So like that includes like having like 5 neighbors above on the original square grid, for instance. In fact, you see, we already had to turn the original square grid diagonal because if we're gonna say any edge or corner, any rows that pass through the centers and the edges or the corners, then we said, okay, well, we have to do that for the square grid too. So that's what that's how we got the diagonal square grid. So yeah, it was just more like a making sure we explored rule sets that were kind of like most closely related. But yeah, there were definitely a lot of other. I mean, there's an unlimited space of rule sets.
But
Yeah.
when Dugan was drawing the squiggles, one of the things that Dugan, you referred to kind of, half rows.
Yeah.
Chase, how did you do the updating? Were you doing only half at a time, or were you doing all at a time?
Yeah. Oh, by the way, I can see Dugan's drawings now because I'm just sharing it from it,
Okay.
sharing the Chrome tab from a different tab, and I'm watching that case. So, yeah, when I did the updating, it's pretty simple. We just go one row at a time. So you see each of those red lines.
Yeah.
Every red line is considered all the cells that are kind of like sliced by it are considered a row. There's also a sort of uh, it gets more chaotic when you consider the fact that, well, um, there are infinitely many ways we could have rotated these cells and had a line sliced through infinitely many cells. So there are infinitely many ways we could have just signed the rows. We just chose the ones that kind of slice through the centers, edges, and corners because we thought those were the most like natural ones. But yeah, there
So
were.
when you were going through a particular line and saying what it sliced through, when it's in between two vertically stacked hexagons, did you count both of them or did you skip both of them?
In between two vertically stacked
Just
hexagons.
take like the second or third line, you just move across. The third line, you go through the middle of a hexagon and then you go between two of them.
Yeah, so we I wish I could do you think I can I wonder if I can whiteboard annotate this.
We can go to a whiteboard if we'd like.
No, and it's no worries. Uh, so if you see the three neighbors hexagons that Dugan's annotating, right? If you see the hexagon at the top left corner, right? So the ones he drew with a dark red circles, right, or like maroon or whatever you would call that color.
Yeah, the brown. Or the
Each of
second row.
those we would just go one cell at a time and just check its three neighbors above, and see all the neighbors above would be done beforehand. And in the case of the very top row, I think we just assumed. Well, we initialized the top row first, right? That's a single cell versus random versus two cells.
Yeah.
So
I mean, would
yeah,
you
each of the
initialize
maroon
the top two rows essentially? This jagged row.
Oh yeah, that's a good question. I think we just, I think for that, we just initialized the very top row. Maybe that wasn't thought through as much, but well, yeah, we just no, actually, yeah, because we just initialized the very top row, and we just, yeah, in that case, the lighter red ones, those would just be initialized to being dead. So, the funny thing is, yeah, that does kind of make it like there are more dead cells in the initial conditions. Yeah, that was how we chose the initial conditions. I actually probably should have thought of that. Maybe like if you're doing random initial conditions, you want to randomize the first two rows, but that
yeah,
that was.
And then the way it goes from there is you want to initialize. I colored the first row black and then the second row red, and then you have enough information to do the blues, and then
Exactly, yeah.
next would be like I'll just call it the black again. Let's see.
Yeah. Yeah, I see what you're saying. Yeah, so yeah, we just set them. We actually just set one row and then we set the rest to dead. That is, yeah, it gets weird though when you start thinking about like for random initial conditions, it's clear how you'd initialize the first two rows. But what if you want a single cell? I guess you just do it on the topmost row.
But in terms of sorting out the connectivity from the geometry, is what you're doing here the same or different than the square grid, but with the square grid doing a step of even phase followed by a step of odd phase? Does that correspond to the same thing, do you think?
Oh, you mean the diagonal square grid?
No, just the regular square grid. And what you do in the regular square grid, on even numbered steps, you update the even numbered cells, and on odd numbered steps, you update the odd numbered cells. It seems to me that that may end up being the same thing, just drawn differently.
Yeah, I like.
Can you
Okay,
say that again,
so
Brian?
as for
If you just, since you're drawing, if you go to the top corner of the square grid, you know, essentially put a red dot in the center of even numbered cells, and then put a blue dot in the center of odd numbered cells. And then put a blue dot. Yeah, no, put the in between the red dots. Actually, that looks black rather than red to me.
Yeah.
Yeah, but just put a different colored dot in between each of those.
So a checkerboard pattern.
Oh,
No,
yeah.
no, you put those up in between in the top row. Right. Yeah, just one up from that. You know, in between the other dots that you've drawn. Yeah, there. So the question is if
With
you
the same color?
alternate. No, with a different color.
Different
Yeah,
color.
put that red.
Like
Yeah.
red, yeah, I see.
Yeah, put those in
Oh,
red.
interesting.
Yes, put those in red. And then the next one, out of phase them and put the reds where underneath the blacks and put the blacks underneath the reds.
Yeah, so
And
that's checkerboard.
yeah. And then the update pattern is black,
Equivalent.
red, black,
That's
red.
equivalent.
Yeah,
Yeah.
and well, that was the question mark. Is that equivalent?
I think that's equivalent.
Black, red, black, red.
You know, because
I know there's a way you can
Yeah,
make
you're
it.
just shifting the,
you're just shifting. It's basically it's the equivalent of a geometric shift. You know, it's just like, you know, taking the hex grid and just pushing everything up, you know,
Yeah.
a
Well, I don't
hexagon.
understand your question.
it's just a visual shift.
It's just it's visually different. But
Yeah.
Just the
the way to
visual.
visually see it is imagine that here, put your cursor at the bottom of the bottom hexagon of the second column on the hexagon grid.
The bottom of the
I don't
second
see.
column.
Yeah, in the hexagon grid. Right. And I don't see your cursor actually.
Here's my cursor.
Yeah, okay, good. Then further down. One further down. Yeah, and imagine that you could just push, you know, push that up a half step.
Oh, I see what you mean now. Yeah. No, it's absolutely equivalent. Yeah.
But you
Yeah.
know, Brian, the thing that so I was like, I see that here, right? But the thing that is difficult to understand then is why does Rule 30? I mean, Rule 30, if in the square implementation, does not look. You know, you can't just push some of those, you know, every other column up a little bit, and then you suddenly get Rule 30 to look like it's striped. There is something about this hexagonal grid that changes the geometry
Well,
of what's being referenced.
it's funny because if we're agreeing that these two geometries share a connectivity, the question that you're asking is a question about the connectivity. You know, so why is it that the in the current top left square grid, why is it that the black red update pattern works differently than all of the black reds together? Right.
I'm confused because here, like this black on the second row is receiving its information from the three above it, right?
Yeah, and in fact, when I said on the bottom when you have to push it up, in fact, it's the other one that you have to push. It's the one beside it that you have to push up to make the lines go straight.
I mean, there's a way you can view the graph and all the lines in between all the connections, but that won't change the topology. There's an inherent topology.
The claim, which I guess Ellie is confirming, she's saying the same thing, is the connectivity is the same in the square one and in the hexagon one. It's just being drawn differently by being pushed a little. You know, it's essentially, it's taking what you have in the hexagon one and straightening the lines.
Yeah, I'm not sure if I'm not sure if it's the same connectivity and drawn differently, because I think that if you just push the second corner, the bottom cell, I think that some of the cells are going to have their to the left and right will be their neighbor rather than cells above them. So that's an entirely different connectivity, even though it's now on a square grid. So it's no longer the 3 above it. You're going to have sometimes it will be looking at its left and right neighbor. But
Well-
what happens is, it will still work out in a way that there's
So what's changing in this, and what's changing in the change of update pattern is in the traditional update pattern, the 3 that you're coming from are all at the same moment in time,
Yeah.
right? Where in the black-red update pattern, the red one is referring to an earlier black, not the current black,
Mhm.
right?
Yeah.
And that shift in time is doing something interesting. It's not obvious. The thing is to get back to, XOR being an even odd rule. At some level, it's not surprising that the even odd magic of it hasn't been broken by that.
Mhm.
You know,
Yeah, XOR still does XOR. It
XOR still does
right?
XOR. What's being XORed is a little bit different. So,
Mhm.
yeah, you'll find some difference in nuance, but in the big picture, it really not clear that it should change that much. But anyway, all very interesting.
Yeah, that's why I think that XOR, I have this idea that, it almost doesn't matter what your 2 references are as long as they're consistent. Because XOR is magic.
Well,
Yeah, Elliot, I definitely
but the thing that does matter is if you go from 2 neighbors to 3 neighbors, that will make a difference.
Right, for sure.
Right.
Yeah.
If I understood, Ellie, if I understood what you were saying correctly earlier, is if the neighbors are being picked like biased to the left, then the whole pattern is going to shift to the right or something, and vice versa.
Yeah. 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 But it's going to have that Sierpinski-like
It's going to have that
presentation.
Sierpinski-like look.
Yeah, which is the XOR.
It almost is tempting to say, so I don't know if we could program this now, is we should just then, rather than shifting it to the left or the right, have the cell that it's referring to be 1 over, being,
Yeah.
above and or skip above and do the XOR to the 1 to the left, 1 to the right, and 2 to the right, and see what you get.
Yeah, exactly.
I'd guess that it would be a Sierpinski something, but a Sierpinski mix.
Yeah. I'm eager to see what it looks like. But another thing that strikes me about seeing some of these rules on these different in these different geometric systems is that reversibility. Some of these rules which are not reversible on a square grid look reversible on other grids. It's really interesting to think about that.
So do you mean time reversible or?
Yeah, like rule 30 looks reversible in some sense. We can on a hexagonal grid, because it turns everything into kind of diagonals. What's and I think there's a sort of false sense of reversibility because you never know when you're going to run into that wall where it suddenly turns. But there's a sense in which we get a more the different geometries kind of lend themselves to this this idea that we're in a much more rational system than we might actually be.
So
Yeah,
is this topology equivalent to the one below, to the hex grid?
Oh yeah, with the diagonal squares.
Yeah.
Yeah, I was gonna bring that up. If you look on my community post, Rule 90 on the diagonal square grids looks like the same as Rule 90 on the hexagon grid almost. I am wondering. I've also been wondering that a little bit. I think it might be the same exact graph. It might just be a less pretty way because I like to look at the hexagons better personally than the diagonal squares. So.
But that's interesting.
Which is just like time going at an angle rather than kind of across, right?
Mm-hmm.
Was it reading that people suggested to everybody that Conrad Zeuss's computing spaces? Do you know this paper?
No, Dugan.
He was
It's such a good.
he was talking about cellular automata physics before Stephen, and one of the things that he was suggesting is part of the paper. The paper is kind of hard to read and it's a bit obscure, but he basically was talking about reversibility and the thing that he had in a way that it's amazing. It's an echo of just what we were talking about 10 minutes ago, a two-phase updating rule. And what he was suggesting is that the physical analogy is one step's positions the velocity step, and the other is the momentum step, or something like that. And
Interesting.
by breaking it into two different phases, it makes it more easy to be for it to be made reversible.
Interesting. Oh yeah, I think I've heard of something like that before. It sort of reminds me of like,
Well, the guy was, I don't know if people, all of us have been following a lot of Stephen's stories. If you heard the story about him trying to find the basement, trying to find a computer in the basement of a house in Berlin. Right. The guy who made that computer ended up being invited to the States by Ed Fredkin in the 60s. And what Ed had Conrad do when he got to the States was translate his very early cellular automata paper from German to English. And it's an interesting work. It's kind of old and obscure, but it's still kind of very much in the zone. I don't think Stephen thinks very highly of it, but you'd have to ask him directly.
yeah. So you were saying like when you have a position step and then a velocity step that
Yeah,
alternate.
and I may be getting that wrong. Basically, the things that I remember is that there were two kind of steps. And if you have two kind of steps, it's easier to make things reversible.
No, yeah, that does remind me of something called leapfrog integration, which is related to the finite difference method, which is used to make some of the wave equation in cellular automata that works really well and related ones. And I think, if I'm not mistaken, leapfrog integration was like, I think is more numerically stable, and it may have been more reversible than just straight forward Euler integration. And I think leapfrog integration used like two different kinds of steps. I might have been mistaken though. Anyways, where it was like it was no, it wasn't that. It was my bad. It was that it was centered on the it's sort of the way it defines it was, instead of just an explicit next step equals previous step previous plus position plus velocity times delta time, it was kind of implicitly defining the future step and the previous step to be equal space from the current step, depending on, I don't know, it was something, yeah, it had a more centered stencil, but anyways, I digress. All right, well,
Sort of.
anyways.
Actually, before we move off this topic, Step Sideways is Marvin Minsky in the early 60s,
Mhm.
claims that he found this by accident. You could make a very stable circle algorithm that could be used to make a very stable sine table. If you take the usual rotation and be stupid about what it's doing and update it in series rather than in parallel.
Mhm.
And this, I think, very much, very likely that this and leapfrog integration are revealing the same thing.
Uh-huh. So it's like a more centered on the current point in time, instead of just thinking
Well,
about the next.
I don't think Marvin claimed to have understood it as much as noticing that it happened. And what it is, and I've actually used this in practice. If you want to make a very quick and dirty sine generator that remains stable, you just do it like this. And this is basically, breaking the rule is you're supposed to update this in parallel. Because the equation that he's doing there, it's basically the rotation matrix for a small angle with
Nice.
with just pushed, one uh, being pushed from sine. There's sine axis and cosine axis, and it's taking the sine axis to be epsilon and the cosine axis to be 1.
Interesting.
And for
Interesting.
some reason, with that sloppiness, you get a better result.
Huh. Yeah. Okay, I was wondering why it was such a perfect circle. But yeah, if it's just it's that rotation matrix for a small angle, then yeah, I see how.
But I did try this at home. You could try this at home. You could compare this to an actual rotation, and you could find that in certain zones it's remarkably stable, and you could show that it's stable. But usually, when Marvin was first doing this, it was on a computer with fixed point numbers. All you need to show is that the state of the thing gets back to the same fixed point numbers, and you know that it's just going to continue to go around.
Mhm.
Where if you do it with floating point, it's harder to prove the stability because you don't necessarily get back to the exact same place.
Yeah. Yes.
Okay,
I
this is a
eh,
bit far afield, so
yeah.
maybe.
Yeah.
I like that. I
Where
like
were
that. So
we?
I think the
as long as
similarity, yeah,
this delta here, this dx or this d is small enough, then you'll approximate a circle by just applying this transformation rule.
Yeah, and the thing that you could do, it really it's 10 minutes to just hack this up in Wolfram language. I did try this. In fact, was even thinking of using this to do, a simple music generation because it's very quick and dirty sine waves. It turns out to not be that good for that particular purpose. You don't have fine enough frequency control.
Huh.
but is this another example in some sense of like the idea that the rules are the rules and the geometry of the system in which we apply the rules can kind of create a different is actually another entity, and when you bring them together you get unexpected results.
Well, I
Sometimes
think
it's more harmonious than others.
I th to the extent that if you're trying to find a way to connect this to what we're really doing, this is a place where Marvin did this in a complete discrete world, assuming the absence of continuity, and that worked in his favor.
Mhm.
And to just complete the story, here's something that is almost but not quite true. He was doing this to help his students writing the very first computer-based graphical game, Space War. Because you may notice that it says on PDP-1, which it was, the PDP-1 at that era is when Space War first got put together.
Yeah.
Hmm.
Elliot, can you share your beadwork? So, Ellie is an artist and does a lot of beadwork and has done a lot of cellular automata beadwork, especially on.
Yeah, I've seen a little bit of I've seen a little bit of your work. I wonder, how did you define the rule sets and neighbors? Or is it
um
handy?
it's just like your hexagonal one. This
Mhm.
is can you see?
Cool, very cool. Mm-hmm.
That's rule 90.
Mm-hmm.
I stuck in some inclusions, like just to sort of show off the pockets of reducibility where I knew, what was going on, so I could put in other things. So those larger dark areas are just me kind of demonstrating to myself that I could predict the rules. This one is a very simple. It was like basically because it's three, you can see that it's just kind of three single seated Sierpinski triangles.
Very cool. Very
This
cool.
one,
Awesome.
they're all rule 90.
Ooh,
This one,
my favorite, rule 90. Yeah,
yeah,
that's a
no, it's absolutely the best. This one also rule 90, what with yeah, you can kind of see I introduced a little bit more noise in terms of errors, and the initial seeds started a bit later, and I put a few different seeds in there.
very cool. Very cool.
Yeah, and this one was maybe the last one we'll show, which is these are teeny tiny beads, but also rule 90. So.
Very cool. Yeah, rule 90 is the actual best.
Well, yeah, right now I'm experimenting with 105, which
Yeah.
it has a very elegant kind of heuristic expression, which is basically if you're thinking about a hexagonal grid like the one that we were adulterating so aggressively earlier. If the two side beads are the same in rule 105, you use the opposite of the center bead. And if their two side beads are different, you use the same as the center bead above. Well, I say bead, but I mean cell when I'm pointing at the thing. And it's kind of like it's sort of XOR-ish, but not exactly. And so it's very interesting. It's actually quite a boring rule in some sense, because you basically get kind of a polka dot pattern if you start with really simple conditions. But if you start with random initial conditions, you get some more interesting kinds of shapes. And the patterns all want to kind of create this sort of there's some way that you get a kind of harmonic convergence. I'm using words in a more artistic way rather than in a scientific way right now, but you do get this sort of sense of a harmonic convergence with rule 105 that's rather surprising. But I don't have work right now that I can share that demonstrates that, but I should have some work soon to demonstrate that.
Yeah. Yeah, we could also probably just test it out on the
Yeah, exactly. Well, that's why so when I saw your paper, I was eager to get a hold of the code behind it, because I want to look at my 105.
Yeah, you're gonna have to do a little bit of coding to
Okay.
my code here, but if you get the hang of it, yeah, it should be able to
Okay, can you share back your code?
Yeah.
All right.
Yeah, I'll share the I'll just share the
what rule did you say? 105?
yeah, here we go. I think this is the one.
Yeah, I think it's 105.
I got 105
Yeah.
here. It's great. Yeah, this is whoa, okay. I was like, why is there a diamond? That was just the periodic.
That's just, but yeah.
So this is just wait, what initial conditions did I put? I have not used that.
It looks like it's like
a single.
That's a single life cell. Wait, that can't be right.
It's correct.
The first row is a single life.
Oh, oh wow, that is wonky.
Yeah.
Okay, right, because it's
crazy.
Kind of like right. And if we do random conditions, you said that would be pretty interesting.
Yeah.
Let's see here.
I actually set things up with, I don't mean necessarily really random, but like I do kind of an organized initial condition. But
interesting. Yeah, you could also if you really want to get into my my code here, you can set whatever initial conditions you like if you set the rate.
Ooh.
Oh, interesting. Oh, that is very. Oh, wow. I have not seen this one before. Actually, not gonna lie.
I'm so happy. It shows you exactly what I was talking about.
Yeah, the periodic boundary conditions are creating kind of like a diamond type sort of. If I kind of see a diamond going on here, which unfortunately I know is just because of the periodic boundary conditions, but that's very interesting.
Oh,
Yeah,
I see what you're saying. Yeah.
Yeah. I don't know. I just
see it's very sensitive to those interactions. Really want to create organization. I mean, I
Interesting.
don't think, yeah. I think that actually the periodic boundary conditions and the boundary conditions are very relevant to, examining these patterns. Like that's how these rules, are working in nature, right? Like they aren't unbounded, right?
Yeah, actually, I also have to I have to take that back. When you have random initial conditions, then I don't think periodic boundary conditions change what you see much, because it's basically just random. The same randomness repeated, which shouldn't have a very big effect unless you had a very small width. Anyways, it's kind of like it's the same randomness repeated, so locally it looks the same as whether or not you have periodic boundary conditions if you have random initial conditions. Anyways, very cool, very cool. All right.
150 is also kind of cool, but I'll leave you to do.
Plug it in.
Okay,
Plug it in. 150. Let's go.
let's do it. Control. Yeah, I might need to add some better comments on how to animate my code to set the rules numbers. But yeah, other than that. I'll give it a, oh, whoa.
Oh,
Interesting.
nice.
Oh, wow. I have not seen this one before.
So
Let's see.
150 is basically like 105, like I explained, but when the two side cells are the same, you use the same as the middle, and when the two side cells are different, you use the opposite of the middle.
Uh-oh.
Oh,
I think I crashed I crashed my note. Yeah. Oh, I think we oh yeah, here we go. It's still here.
Okay, good.
Cool. Awesome. I see. Very cool. So when the two side cells
Oh, but it stopped sharing.
Yeah,
On
stop
Zoom.
sharing.
Okay, cool. Let me just reshare my
You're treating the internet like a dump truck.
anyways, yeah. When we share
There we
the
go.
I'm sorry, when the two side cells are the side cells are the same, then it uses the same as it, and when they're different, then it uses the opposite, did you say?
Yeah, so when the two side cells are the same, 150 uses the same as the middle. When the two sides are the opposite, are different, it uses the opposite of the middle. And that's
Cool.
150. And 105 is sort of like that. When the two cells are the same, it uses the opposite of the middle. And when the two cells are different, it uses the same as the middle. And
Okay, so these are
so
like XOR and XNOR.
kind of ish. Yeah. They're sort of gated versions of XOR. I'm sure I'm using that term incorrectly, but it's a more complicated version of XOR because it refers to a third cell, where XOR only refers to two things.
Okay,
I
so
see.
why does each you can trace like each color downward, and like each thread just gets like wider and moves to the left and right and gets shorter and wider and narrower, but it never like gets cut off. Nothing gets cut off.
This thing, this like zigzags thread, are you talking about?
You can
see my mouse?
trace trace a particular
Yeah,
color
yeah.
downwards, and they just get shuffled around, but they never like get pinched.
Oh yeah, I do see that. Yeah, each thread kind of does. Well, yeah, none of the threads they never get clipped off. Yeah, I see what you mean. Like the
Yeah,
yeah, that is pretty interesting. That is pretty interesting. Sometimes they
that's really cool.
oh wow,
And
yeah,
they
I
kind
did
of
not
shift
see that.
around chaotically. You don't really know how big or wide something's going to be. Although you do see like patterns of thickness going across diagonally for some reason.
Yeah, I also the patterns of thickness going up across diagonally. Like here we have a lot of zigzag, and then here we have a lot of squares, I'll call them. So,
Yeah, these rectangles pop up.
and here we have a lot of stripes. Oh, that's weird. That is weird. that
Yeah.
is- yeah. Yeah. Let's see. I definitely would say the three neighbors hexagon was probably one of the most interesting grids I explored out of all the ones. Yeah. Anyways,
Awesome.
yeah. Cool. Well, yeah. I think cool. Yeah, that
That was super
and,
amazing,
so
Chase. Thank you so much.
any other anyone else have any other questions or yeah.
For sure. Thank you so much, Chase. And thanks for everyone tuning in
Thank you.
on the live stream. Ellie, thanks for
Thank
joining
you.
us and showing us your beautiful artwork.
Yeah, awesome. Yeah. Thanks for sharing
Yeah.
the artwork.
The two
It's cool
Brians,
that we
thanks
Really
for
happy to
showing
have a
up.
chance to. Yeah.
discovered the same Rule 90 is definitely my favorite. Yeah.
Yeah, but
And-
105 and 150, I think they're vying for your heart now.
Absolutely. Yeah. I think I sent the published notebook, right? And you also have access to my community post, right? So you might have to get your hands dirty a bit and crunch some code a bit before you can get the patterns going. But once you do, it can be pretty rewarding.
Yeah, for sure. I'll be taking a look at that myself, I'm sure. And
Awesome.
we'll wrap it up. Thanks for coming.